So once we have trained our speaker classification models and after we have tapped the embeddings from them, what next? We have to do some kind of scoring, right? Without doing scoring, we cannot do any speaker verification task. So under scoring, we will discuss 3 different techniques. One is PLDA, which is probabilistic linear discriminant analysis. Next is a simple cosine scoring, and then finally TESA, which is by our speech lab at IIT Madras. TESA is actually transformer encoder speaker authenticator. Okay, these are the 3 techniques which we will see under the scoring mechanisms. First one, PLDA. So in every scoring technique we should have a trial pair, which is nothing but a set of 2 utterances, and for these 2 utterances you would have extracted the embeddings, and these 2 utterances may be from the same speaker or from the different speaker. So the utterances, when the utterances are from the same speaker, we call it target access, and when they are from the different speakers, we call them as imposter access. So in PLDA training, after the extracted embeddings, after the embeddings are extracted, we first perform an LDA, which is a simple linear discriminant analysis, and then we do a PLDA training, and with the trained PLDA model, we get the scores for the trial pairs. We will not get into the details of this PLDA training more because it is much more involved, but I would like you to know what LDA is. So if you have features distributed like this, okay, it is a 2-dimensional features. So let us say they are distributed like this, and these features belong to some 4 different classes. One is this brown one, green, navy blue, and the light blue one. LDA, what it does is, it tries to find a optimal projection direction such that we can separate out the classes. Okay. So here, if this is the projection direction, we can see that this class values gets projected with this class center, and the values get projected like this. For green, the features get projected like this. For the navy blue one, again something like this, and for the light blue one, it is something like this. And we can see that, okay, I can happily put some thresholds to say, okay, if the features lie from this region to this region, then it belongs to the brown class. If it belongs, if the feature lies in this region, then it is the green class. If the features lie in this region, it is the navy blue class, and if it lies in this region, it is the light blue class. Okay. If I take a projection direction like this, okay, say this is another projection direction I am taking, then what will happen? This whole thing and this, they will get like together projected in this region, right? So the brown ones will get projected like this, and this green ones are also getting projected on top of it, and even these navy blue ones will also get projected here. So there is no class separation possible, they all get mixed up. So this is not an optimal projection direction for what? Class separation. Okay. We are worried about projection directions for separating out the classes. Okay. So this is not an optimal projection direction, whereas this seems to be somewhat optimal. But LDA does it mathematically. We are not going to like draw these projection lines and find out, rather it does it mathematically. PLDA does something more on top of this LDA, which we will not discuss in this course. Okay. If you are interested, you can go and see the literature. So after this LDA, we perform the PLDA training, and with the trained PLDA, we get some scores, and on the scores you set some threshold to figure out whether I will accept the trial pair as from the same speaker or from the different speaker. The next scoring technique, let us skip this. Okay, we are not going to look at this. The next scoring technique is cosine scoring. this is the simplest scoring method, I would say. So you just take the trial pairs, you extract the embeddings, so you will have 2 embeddings for one trial pair, and then you do a simple cosine similarity. What is cosine similarity? If in a vector space, 2-dimensional vector space, let's say, if one embedding is lying like this, let's call it P, and the second embedding is something like this, let's call it Q. What this cosine similarity does is it finds the cos of the angle between them, cos theta. So that's what your cosine similarity does, and it's given by P dot Q, the dot product between the two vectors P and Q, which is nothing but your embedding vectors, divided by the magnitudes of both the vectors, which is in detail given in the right side of this formula. So this is the simple cosine scoring technique, and then you will get your scores because it is cos theta. The values possible for the scores are -1 to 1. Okay, the scores cannot go beyond this range. So the next scoring technique is TESA by Speech Lab at IIT Madras. TESA means Transformer Encoder Speaker Authenticator. So the name suggests that it is made of transformer encoder, and it is inspired by BERT. BERT you must have heard if you have taken courses on NLP. If not, I'll briefly explain what BERT is. BERT is actually bidirectional encoder representations from transformer. So this is what BERT is. So this is going to use a transformer encoder to do something, okay. So BERT is an architecture that was introduced for the purpose of self-supervised training. And once this model is trained in a self-supervised fashion, you can perform lots of tasks with this, okay. So what is self-supervised? You don't give any supervision, the supervision comes from the data itself, okay. There is no external supervision. So how is this BERT trained? You will take inputs which are 2 sentences, okay. They may be consecutive sentences or they can be different sentences, okay, which means they need not follow each other. So we have 2 sentences, they may follow each other or they may not follow each other. So here the 2 sentences are, my dog is cute, that's your first sentence. He likes playing, this is your second sentence. So here you see that this playing is split into two parts, okay. This is called word pieces. So playing is split into play and ing. So this is done to reduce the word piece count the model can handle, which means if I have singing, I will split it as sing and then ing, okay. So some commonalities in the words are being exploited to reduce the word piece counts. And so there are 2 sentences. Along with this, you have some special tokens which are this CLS and SEP, okay. CLS is used to mark classification, SEP is to mark separation, okay. So separator token, it is used to say that the first sentence has ended. So here my dog is cute, this sentence has ended, we have one separator token here. He likes playing, the second sentence has ended, so again we have a separator token. This CLS token, the use of it, I will come to it later. So once you have this word pieces, you cannot feed it to the model as such, because the model is not going to understand what my means or what dog means, okay. Model can understand only some vectors. So what you will do is, you will convert this word pieces to some learnable token embeddings. So my subscript means it is the learnable embedding for my, okay. Similarly, a learnable embedding for CLS. What does this E mask means? I will come to that again later. So similarly, you have the respective embeddings. Okay, here it is masked. Let us come to this again later. You have, okay, the respective embeddings are here. So you see some embeddings instead of E subscript dog, okay, which is the embedding for the word dog, you just give it as E subscript mask. In the sense, I have masked this token. I am not passing this token for dog, rather I am saying that it is masked, okay. To the model I am saying this token is masked. Similarly here the likes, this is also not passed, rather I just say that it is passed, and wherever you mask it, the embedding for mask is passed, okay. So here the embedding for mask is passed instead of the embedding for dog. Similarly, the embedding for mask is passed instead of the embedding for likes. This is how you prepare your embeddings for BERT training, okay. And once that is done, you have something called sentence embeddings and position embeddings. Position embeddings, it's the normal embeddings that you see in transformer encoder. So it's just listed as like E0, E1, E2 till E10, because totally there are 11 word pieces here, okay. So the positions start from 0 and 10. The new thing that you are going to see is this sentence embeddings, okay. This is to say that my dog is cute and until your separator, it corresponds to one sentence, okay. You want to give that information to the model. So what you do is you had a new embedding called EA, okay, E subscript A, which is again learnable to the tokens till this first separator, and E subscript B, which is again a learnable embedding for the second sentence until this separator, okay. This is how you prepare your data, and once this is all added and the embeddings are all set up for the masked ones, okay, and finally the data is prepared, you pass it to the transformer encoder. Okay, after passing it to the transformer encoder, we must have some objective, right? What are we going to do with such a data preparation? We are going to perform two tasks, okay. There are two tasks. The first task is called the next sentence prediction, okay. The loss function is going to be the sum of two loss functions, okay. So one is corresponding to the next sentence prediction task, another one is corresponding to the masked token prediction task. Let's first see what is next sentence prediction task. So so you know that when I am passing the input, it is a set of two sentences, and the two sentences may follow each other or they may not follow each other, right? So the next sentence prediction task, what it does is, it taps the CLS token after the transformer encoder layers, okay. The corresponding one is somewhere here, right? So and if both the sentences looks like they are following each other, you will try to train the model to say that the CLS should go high, right? You will say that CLS is 1. If they are not following, then you will say CLS should be 0. So that is your next sentence prediction task. Let's come to this masked token prediction task, okay. So we prepared the data such that instead of passing some tokens, we rather passed the token corresponding to mask, right? Here the dog is masked and the likes word piece is also masked. What you will do is the corresponding encoder output, right? After passing this data to the transformer encoder layers, the third element, right? So you will tap the third element after the encoder, okay? Third element you will tap, or if I name it as 0, 1, 2, it is the second element. So this is the 0th element. This is the second element, okay. I tap it and I predict it as dog, okay. Similarly, I will tap the 7th element after the encoder part and make it predict likes. So this is called the masked token prediction. I have masked the token here, I am asking it to predict what token should it actually be, right. So this is something like fill in the blanks, if you see, okay. So what it does to the or how this kind of training is helpful is that it helps the model to understand the language. It is able to fill in the blanks, so it understands the language. It is able to tell, once it is trained, I am saying, once it is trained, it is able to fill in the blanks. So it is knowing the language. Another task, it is able to say, okay, whether two sentences follow each other, are they related or they are not at all related, so it is able to tell that. So it is some kind of language modeling. That's what your BERT is trained to. Once it is trained, this trained model is taken and used in many downstream tasks like machine translation kind of stuffs, okay. So this is BERT, and this served as an inspiration to TESA, and we will see how we modified this to make our objective or to get the objective of speaker verification done with TESA. As mentioned before, TESA is inspired by BERT. In BERT, we had two tasks, okay, while we trained the model, it was trained to perform two tasks. One is next sentence classification and masked token prediction. So for TESA, the inspiration comes from the next sentence classification task. We are not worried about the masked sentence, masked token prediction task, okay. So in BERT we had word pieces, and those word pieces were converted to some embeddings, and then we added some sentence embeddings, position embeddings, and fed it to the transformer encoder, right. So instead of word pieces being converted to some embeddings and then they are being fed to the transformer encoder, we feed the S vectors to the model, okay. So for that purpose, a trial pair which has two utterances, utterance 1 and utterance 2, if they are of longer lengths, we chunk them into some small size chunks, okay. So here it might result in 4 chunks, this could have resulted in 3 chunks. You pass it to the S vector model, and then you will get one vector corresponding to each chunk, okay. In the normal S vector, what we did is we averaged them out, but for the purpose of TESA, we are not going to average, rather keep them as a set of S vectors with us, okay. So utterance 1 S vectors and utterance 2 S vectors. We take these vectors, okay. So here you can see utterance 1 S vectors and utterance 2 S vectors. So they can be of different lengths because each utterance could give you different number of chunks. So here it is L and here it is M. You pass it to some batch norm, feed it to a feed forward neural network, and after this you add the CLS token, separator tokens, okay. So 250 cross L, this is the dimension we have set, okay. From the S vectors you would get 512, but we are taking it down to 250 for this model. After this you just add the sentence embeddings in the BERT, right. So here we call it utterance embeddings, okay. So we add something called the utterance, sorry for the spelling, utterance embeddings, okay. And we do not add position embeddings, no position embeddings here, for an obvious reason, because there is no continuity, it is just a set of S vectors, right. So we have not added any position embeddings. So utterance embeddings, you see that it's U1 till this first separator and U2, okay, till the second separator. U1 and U2 are learnable. Similarly, CLS is a learnable embedding, and for separator also it is made as a learnable embedding, and then you pass it to the encoder layers, transformer encoder layers, okay. Transformer encoder layers, fine, okay. So at the end you will get what? You will get some k elements, right. So L plus M plus 3, that is what you will get, L plus M plus 3, 3 is like 1 CLS and 2 separator tokens, that is your k, okay. Because we are interested only in saying whether these two sets of S vectors belong to the same speaker or not, we are worried about the corresponding element of the CLS alone, okay. So E1 is the element that corresponds to the CLS, we take that element alone and pass it to 2 feed forward neural networks, and then finally to a output layer with just 2 nodes, and then perform a cross entropy on it, okay. Okay, once this model is trained, okay, we will feed with different trial pairs, okay. So many, they are trained with lots of trial pairs. They may be from with 50% of the trial pairs being from the same speaker and 50% from a different speaker, and this can be a huge, this is a huge set of speakers, like 7,000 speakers. You imagine the number of possibilities that you can create for the same speaker and a different speaker, okay. So once the model is trained, we have to get some scores, right? Like how are we going to get the scores? So you, during the testing phase or during the scoring phase, what you do is you pass a set again. You have two nodes, right, in the output layer. So before the softmax is done, right, what you will have is the logits, which is nothing but before softmax. Okay, you take them. So one will correspond, or one will go high when it is from the same speaker, one will go high when it is from a different speaker, right. What you do is you subtract the logits of the different speaker from the same speaker, logit minus the score is equal to, okay, minus different speaker logit. So this is how you get the scores. Once you have got the scores, what is the next step? So we have got the scores by three methods, right. One, the first technique is PLDA, second technique was cosine scoring, and the third one that we discussed is our in-house TESA. So we have got the scores. After the scores, you have to find some threshold, and you have and how do you decide which model is better? Some evaluation metrics has to be there, right, to say that model A is better than model B. So we will discuss how the evaluation metrics are working, okay, in the next set of slides. As mentioned before, a trial pair is a set of two utterances. These two utterances may be from the same speaker, we call it as target access, or from the different speakers, we call it as imposter access, okay. Let us say we have some n trial pairs, then if S1 to Sn are the corresponding scores, okay, these are the scores, okay. If these are the scores, what you will do next is to create a sorted score list. Let us say from this is the lowest and this is the highest. Okay, intuitively what should it mean? If the score is like lowest, then towards low, okay, towards low, then it would mean it's an imposter access, right? And if the score is high, then it's a target access. There is a high chance, okay, I won't say that it will be imposter access or it will be target access, but there is a high chance that it will be a imposter access if the score is low, and there is a high chance that it will be a target access if the score is high, okay. But where to set a threshold? We have to put a line, right, okay, and say, okay, below this I will say that it's an imposter access, and above this I will say that it's a target access. Some line we have to draw. So that's called the threshold line. So let's say I have put a threshold like this, okay, somewhere here, which means all these trial pairs will be classified as what? As imposter, because this I am taking as the low and this is high. These are classified as imposter access, and these would be classified as target access, which means it's the model is saying that these are from the same speaker and these are from different speakers. But won't there be any errors? Because it's just a model, okay. So there will be errors. There is a slight chance that same speaker trial pairs are present here, and there is a slight chance that different speaker trial pairs are present in this region also. So those are your errors, right. So if a trial pair has a score lesser than the threshold, the verification system will try to classify the trial pair as imposter access and target access otherwise, but it may falsely accept an actual imposter. So that this error actually happens in which region? This region. Or it may falsely reject an actual target. This error is happening in this region, okay. So these are the two system errors that are possible. And how are they quantified? They are quantified like this: number of false acceptances. Where do the false acceptance actually happen? In this region, okay, divided by the actual number of imposter accesses. This is called RFA, and you have RFR, which is number of false rejections, which usually happens in this region, divided by the actual number of target accesses. Okay, this is the ground truth. This is the ground truth, and these are the errors made by the model. So these two metrics, okay, or I will say these two errors, they form the basis for the two different metrics that are used, which is EER and min DCF. Okay, these two metrics are based on these two error rates. Let's first see what an EER is. Okay, so to get an EER, you need something called a DET curve. DET means detection, error, trade-off curves. Okay, detection, error, trade-offs. So what you will do to get this basic curve is, you will vary this threshold. Okay, you will not keep a fixed threshold, but rather vary the threshold, vary it. So first you will keep it here, then you will move it here, and then you will move it here. Okay, not in a quantified fashion, but in a continuous fashion. Okay, and you will get the RFA and RFR for different thresholds and plot them. Okay, so when you vary the threshold, what will happen? The RFA and RFR will vary. So this is how the traces are, and I have given the curves for two different models. There are two models, model A and model B. So the blue line corresponds to model A and the orange line corresponds to model B. Okay, so to this DET curve, what you do is, you draw a 45-degree line. This is a 45-degree line. Okay, degree line. Okay, and you see where they cross this curves. So you get 2 points. Whichever has a low value, okay, that model is better. So this is called equal error rate, because this is the point where RFA and RFR become equal for that particular model. Equal error rate of a model is equal to the point, or the is actually the value at which the RFA and RFR equals for that model. Okay. So this is your equal error rate. This is our metric 1. So based on equal error rate, how can we say whether a model is better? Whichever model has lesser EER is a better model. Okay. Moving on to the second metric, DCF. It's given by this: CFR into RFR plus CFA into RFA. Okay. CFR is nothing but the cost of false rejection. CFA, cost of false acceptance. Okay. These cost values, they vary based on the practical applications. Okay. Sometimes the cost of false rejection can be high. Sometimes the cost of false acceptance can be high. It depends on the application. Okay. So depending on the application, you set some values for the cost. Okay. And when you multiply the RFA and RFR with them, you end up with DCF, which is nothing but the deduction cost function. Okay. To this cost function, there is one more entry that is to be like brought in, which is called the P target, which is actually the probability of target access. What it tries to incorporate is, okay, the previous one is the cost function, it's well and good, but how much probability is there for target access and how much probability is there for imposter access? Based on that, your cost function will vary, right? If there is more chance of imposter access, then the cost function should give more weightage to the, which one? Imposter false acceptance, right? So this one, right? More weightage should come to this term. That's what will happen here. If you see 1 minus P target, because there is more chance for false or the imposters, this probability will go high and this term gets more weightage. So, it is a weighted combination now. So, to bring in that effect, the P target comes into picture, and this is your deduction cost function, the final deduction cost function. This is our metric 2. The actual metric is min DCF. The RFR and RFA values, which actually gives minimum values to this DCF, is taken as the actual RFA and RFR corresponding to the min DCF. Okay. This is our second matrix. So, we had two metrics, one is equal error rate and another one is the min DCF, both based on two errors, which is the false rejection rate RFR and false acceptance rate RFA. Okay. Okay. So, wrapping up speaker verification, what all did we discuss? First, we discussed what is speaker verification. Okay, and its difference between speaker identification, right, okay. So, speaker verification tries to verify, is this person same as the identity claimed, is the same, sorry, identity claimed. Okay, this is the question answered by speaker verification. What does identification do? Who is this person? There is no claim. That is the thing, important thing, difference between your speaker verification and identification. Okay. After this, we saw about two conventional speaker verification systems. One is the UBM GMM based, another one is also an UBM GMM based, but something more happens there with super vectors and stuff called the I vectors. And then once the era of neural networks started, we moved on to something called neural network based embeddings. Okay. For this, what did we do? The first step, we have to train a speaker classification architecture. Okay, classification. After that, you extract embeddings. Okay, from those architecture. How many architectures did we see? We saw X vector architecture, R vector architecture, and our in-house S vector architecture. So, once we have extracted the embeddings, the next step is to do scoring and setting a threshold, right. For scoring, two conventional techniques were PLDA, which is probabilistic linear discriminant analysis, and cosine similarity. Okay. And then our in-house TESA, which is transformer encoder speaker authenticator. And then once you have the scores to say whether model A is better than model B or model B is better than model A, we saw some evaluation metrics. Okay. And under that we saw two, one is equal error rate EER and min DCF. Okay. So, this wraps up speaker verification. Next we will start with speaker diarization, where we will see the application of speaker verification too.